Hello guys, welcome to IIT and Gate classes. Today we will be discussing about a rocket propulsion part. Uh, this is a demo session. So I will be briefly touching upon one or two concepts from the rocket propulsion, and we will try to see the kind of problems being asked in previous year Gate from these topics. Okay, okay. Let us jump on to the subject. So I will give you a brief introduction about the rocket propulsion. So in general, the propulsion in Gate Aerospace is divided into like two parts. One is aircraft propulsion, other one is rocket propulsion. So in both of these propulsion subjects, it is important for us to understand the basics of fluid mechanics and thermodynamics at priori. So usually in IGC, the fundamental parts covering fluid mechanics and thermodynamics will be done beforehand before we are moving on to the any of these propulsion topics. Okay, so in today's session, I will presume that like you kind of have a um, background on this thermodynamics and propulsion from your BTech courses. So let us assume that, and we will start our session. So usually when it comes to a rocket, so we will see a lot of mass distribution. So like a rocket is a very huge structure. So like we will be carrying propellants that will be burnt during the flight, and that will give you the thrust, and that propellant mass we will be carrying. There is a structure that is carrying all these propellants, electronic systems, as well as the payload. The payload is something like a satellite, or for a manned mission it can be humans and all. So the payload mass, that is what we want to take it to the some orbit, or to the beyond the atmosphere. So that is the payload, and to carry the payload we will build this structure called as the rocket. So that has a like total mass, what we call is like, initially when you place a rocket on a launch pad, thus that mass we will refer it as the initial mass, or initial mass at the launch. And we will be having a propellant mass. So let us denote it as m naught, that is initial mass at the start, and mp is the mass of the propellant we are carrying. Then we have a structure mass, so that is a support structure. Then we will have a payload. So usually we will be dealing with these four masses. So like when it comes to a system wise analysis, we can have a multiple masses included, right? So now, so we kind of have a brief idea about like what kind of masses we are going to deal with. So now I will move on to the different relations among these masses. The total mass at the start we can usually denote with the sum of all the masses included: the structural mass, the propellant mass, and the payload mass. So let me denote ml as the payload mass, mp as the propellant mass, ms as the structural mass. So the subscripts stands for those terminologies, and we can rearrange it actually. So sometimes we refer it as the final mass of the rocket. Say like I am carrying some amount of propellant. If I burn all the propellants, what is the mass I am left with? So that mass we will refer it as the final mass. The final mass is usually the initial mass minus the propellant mass. Okay, so this we refer it as the final mass of the rocket. Why these masses are important? Because when it comes to a rocket equation, we have a very nice relation between the initial mass whatever we are carrying to the final mass whatever we are having. So they are related in a way that like how much of velocity gain I can achieve. So that is why these masses are very very important. Okay, so now the usual syllabus that starts with the calculation of thrust from a rocket. So that involves a derivation. The systematically we what we do in our regular sessions is like we will take the control volume. So then we will do a volume analysis on this moving control volume system. Then we will obtain the thrust equation. Since like we are not introduced you the fluid mechanics basics yet, so I am not going to discuss about the control volume analysis or the Reynolds transport theorem directly. So instead what I do here in the demo session is like I will take my thrust equation directly. Okay, so I need this equation in the later part of my discussion, so I am just taking the thrust equation directly. So I can write the thrust equation for the rocket as the momentum thrust plus the pressure thrust. So what is this momentum thrust? So we know from the Newton's law of motion, the second law of motion, that says like the rate of change of momentum is nothing but external force acting on the body on the direction of the momentum change, right? So that is what corresponding to a momentum thrust. So how are we getting this momentum change? Because we are burning the fuel, so that the fuel which is burnt, that will be expelling out of this nozzle. What you see here, the converging diverging section, this is a supersonic nozzle. So through this nozzle, that will be expelling out at certain velocity, say like ue, or you can also refer it as the jet velocity cj, or sometimes also referred it as vj, depending on different literature. There can be different notations. Okay, so now, so the momentum is usually the mass flow rate times the rate of change of momentum. It is not just the momentum, right? So so just momentum, we can refer it as mv. The rate of change of momentum is dp by dt, that is nothing but d by dt of mv. So that becomes mass flow rate times ve. So that is having a unit of force, so we refer it as the thrust force due to momentum. The other part that can contribute towards the thrust is the pressure difference at the nozzle exit, right? So we know from our basic understanding that pressure is a point function, or what happens at any given point you can have only one value of pressure. If at all there is a difference in pressure, if you are approaching from this direction and if you are approaching from this direction, the difference will going to contribute towards the net force. So that is corresponding to pressure thrust, right? So at the exit plane, I can have the flow which is expanding, that is going to reach certain value of pressure, call it as the exit plane pressure, and there is an ambient, so that ambient condition will be PA. So in an ideal scenario, this exit plane pressure and this ambient pressure should match, that we refer it as the optimal expansion. But in practical scenarios, they cannot match. So we will be having some part of the pressure thrust that is contributing towards the overall thrust. Okay, so this is how we get the thrust for the rocket equation. And now we are going to define certain basic quantities that is usually used in rocket propulsion literature. So such as we can define effective jet velocity. What is effective jet velocity? Just now we saw the thrust can be written as mass flow rate times exit plane velocity of the nozzle plus the pressure thrust. So let us assume all of this thrust is coming from some kind of a momentum thrust alone. So we are writing this equation into mass flow rate some times some velocity, that is equal to the entire thrust equation m dot ve plus pe minus pa times ae. So now what you have, this velocity, that is an equivalent velocity or effective velocity. This is not, it may not be a true velocity at the exit plane, but so it's kind of an effective exhaust velocity we refer it as. So we can write effective exhaust velocity to be equal to, so if I divide the mass flow rate throughout this equation, that becomes VE plus PE minus PA times AE divided by mass flow rate. So this one we refer it as the effective exhaust velocity, CJ, right? So we can simply write my thrust as m dot Cj. That Cj constitutes both exit plane velocity and contribution from the pressure thrust. So now why this is important, because when we define specific impulse, in specific impulse is one of the parameters that is used in the rocket propulsion literature to compare between different propulsion systems. So how effective is our propulsion system or choice of propulsion system, that is governed by number of parameters. One of the important parameters is the specific thrust. How do we define the specific thrust? We usually define the specific thrust as the total impulse per weight flow rate of the flow. So what is total impulse? In general, the thrust what you have in your rocket propulsion, that can be a function of time. Okay, so the total impulse, how you define this, is a basic physics from your high school physics, you have learnt it. How do you define an impulse? That is force acting for a short duration, right? So if you want to get the total impulse, then you have to have a integration of that function of time over a time period of rocket out, which is operating. So divided by, so again we can have a mass flow rate that can be a function of time dt times g naught. So this is usual definition of a specific impulse, a precise definition, but with certain assumptions. Say like if I assume I have a rocket system that is producing a constant thrust with a constant mass flow rate, so then my specific impulse reduces because it is a constant, right? So if you integrate any constant, it will be just constant outside times time. So that becomes mass flow rate times, this also becomes that time part will vanish, and you only get F divided by mass flow rate times G naught, that is nothing but the weight flow rate. Weight flow rate, we define it as mass flow rate times G naught, right? So this is a force is nothing but mass flow rate times effective exhaust velocity. So I can have a very beautiful relation between effective exhaust velocity and the gravitational constant with the specific impulse. Though the specific impulse depends on various parameters, when it comes to a regular class, we will dig deep into the specific impulse definition. For now, we will take it as a granted, like this is how we find the specific impulse. Okay, so like there are some literatures like Russian literatures where they follow the specific propellant consumption instead of a specific impulse definition. That is simply a inverse of specific impulse. This has something to do with the historical definitions of like a specific fuel consumption or TSFC, thrust specific fuel consumption, in aircraft literature. So they borrowed the similar terminology here. Okay, so now as I said, so the total impulse we are defining in this fashion, and specific impulse we are defining in this fashion. So this can be reduced it to Is is equal to F by m dot times G naught, or which can also be shown as effective exhaust velocity divided by G naught. That is fine. Or you can also write effective exhaust velocity in terms of specific impulse times G naught. Remember, So there is an interesting point, right? So like we define a effective exhaust velocity as VE plus PE minus PA times AE divided by mass flow rate of the propellant. So say if the nozzle is optimally expanded, in that scenario what happens? The exit plane pressure will match the ambient conditions. So in that case this vanishes. So our effective exhaust velocity or the exit plane velocity, they are the same in those conditions. And most of the times in your gate, if they are not specifically mentioning this condition, that means like they are referring to optimal expansion condition, that we can assume safely, if at all it is not explicitly mentioned, right? Okay. So then we can also define certain ratios such as mass ratio. That is mass ratio, we define it as the final mass of the rocket to the initial mass of the rocket, or like as we said, like all these masses they have a relation, like the total mass, the initial mass is nothing but structural mass plus propellant mass plus payload mass. So the final mass I can also write in terms of minus mp, or that is also equal to the structural mass plus the payload mass. So you can play along with these different relations to represent this mass ratio in different forms. That will be helpful in your numerical calculations. Other than that, like the usual definition is final mass to initial mass. And propellant mass fraction is the amount of propellant you are carrying out of the total mass you are having at the initial stage. So this one we are not concentrating now. So this is fine if you remember the mass ratio definition, how we define it. Okay. So similarly, why it is important? Because when it comes to a rocket which is moving in a space, so the ultimate aim for us is how much of velocity gain we can actually get from the given amount of fuel, right? So the purpose of rocket is to keep the payload into a certain altitude or certain orbit or beyond the orbit with a specific um, velocity, because we have to balance the potential energy, the kinetic energy and other energies, so that it can remain in a given orbit, right? So that is a basic physics like you studied. So like you have to balance exactly the centrifugal force and the centripetal force, so that we can keep the object in a particular orbit. Or if I want to escape from the gravitational field of a certain um, body like earth or any planet, if it matters, so then we have to achieve certain kind of escape velocity so that we can go out of the orbit. So to achieve those velocities we have to gain that velocity somehow, right? So this is exactly the equation that governs like how much of velocity change you can expect from the given rocket if you are carrying a certain amount of fuel with an initial mass m naught, and you are carrying some amount of fuel mp, and it has a structural mass ms and the payload mass ml. Then what would be the velocity change you can achieve from that rocket? That's what given by this Tsiolkovsky rocket equation. So in today's demo class I am not really going to derive this equation, simply I am just stressing out the importance of this equation. Then we will see the final form of that equation, uh, just like what we have defined so far. So those mass ratios and other variables in which we are going to represent this particular equation. So this is just a differential equation, so we can, if you integrate it, like we will get the generalized um, equation. So it's just like governing differential equation, we can solve it, right? So how do we solve? So the
Guys,
from
so far, any doubt? Akshay, one suggestion, you keep asking these guys Okay,
Okay,
for
okay,
any
okay.
doubt or any concern. Otherwise, it becomes one way. Yeah.
Ha ha.
So, Sneha, is
Fine.
it clear for now? Nirja?
Yes.
Yeah, we are just giving essence of how we take up subject. So you can see we take everything from scratch, but here since it's a demo class, we cannot go in much depth. Okay.
One
Yeah.
explanation.
Please continue, action. Yeah.
Okay, okay. Yeah. So like, please stop me if you guys have any doubt, or if you have, let me know. So you can either chat or you can unmute yourself and you can ask in between. Okay, it's fine. So now, yeah. So as I said, that is a governing equation we have. Sorry, right? So now we can easily solve this. So if I integrate, so I can easily get the solution for this. So like any differential equation of this form, you know how to solve it. It's a basic math. So if you integrate this one, so you get a change in velocity is equal to v dm by m. So if you integrate that one, logarithm of, so you are integrating from initial mass to final mass. If you apply the limit, what you get, mf over m naught, something like that, right? So that is my rocket equation. So now what is important of this, what is very important in this equation is, like, you see, it all relates to at what velocity your masses are exhausting from the, so like it can be ve or it can be effective exhaust velocity in general, and at what velocity the masses are going out of the system or rocket, and also it connects to the initial mass you are having and amount of fuel you are burnt, because the final mass is kind of a measure to how much propellant you are carrying, right? So you are taking out the propellant from the system. So based on that, you can get how much velocity gain you can achieve. So this is a very, very important relations, one of the important relations in rocket propulsion. So in this derivation or whatever form we have here, we kind of neglected both gravity effect and aerodynamic effect. But in general, whenever the rocket is going from some planet, so there will be a gravitational force that is acting on the body, and whenever it is traveling in an atmosphere, there will be an aerodynamic resistance, we term it as the drag, that is acting on the body. So those things also comes into picture in the final velocity change. So usually these two, gravity and aerodynamic part, are the losses, because they are the resistive forces to the moving of a body away from the planet. So that is why, so we usually have a gravitational loss or aerodynamic loss associated with the overall velocity change what we can expect, right? So any doubt so far? Okay, okay, yeah. So I'm not going to discuss about the nozzle flows. This is more of a gas dynamic uh, part of the syllabus. So like I'm not going into the details of this nozzle flows. Usually what happens, we assume a converging diverging nozzle that is to be operating at a steady condition with an isentropic flow through the nozzle, and we can get a very nice isentropic relations based on the um, deduction of momentum and energy equations. So we can have the relations between a different part of the, say, like inlet to outlet or inlet to throat or throat to outlet and all. So we can play along with, so we will get a very beautiful relations between different thermodynamic variables. So we can calculate, if I know the conditions at one station, I can calculate a conditions at any part of the nozzle. So that is a very interesting derivation we will do in the gas dynamic sessions. So now, so we will at least I will assume that you guys have a rough idea about gas dynamics topics. or isentropic flow through the ducts. So we will I will straight away move to the final equation. So like areas related to a Mach number at different sections as a function of the gas whatever you are using. So see, it is just a function of Mach number and the type of gas we are using, so we can easily calculate, right? Or if I given the area ratio of the nozzle for a given geometry of the nozzle, I can calculate what is the Mach number I can get at the exit plane of the nozzle, or what is the Mach number at any station of the nozzle, and those things we can easily calculate from these relations, isentropic.
Yes. So Akshay, I will just interrupt here. So you guys
Yeah.
are understanding the importance of basic subjects, right, guys? That's why IGC always starts with basic fluid mechanics, thermodynamics, gas dynamics. Then only we teach core subjects. Clear, Sneha? Because there are some institute, they directly teach you propulsion, aerodynamics, and all flight mechanics and everything. But that's how result won't come. Okay, for many of average students. Nirja, are you understanding this the point, Anand? Because here whenever you learn in aerospace core subjects, by default you must know basic subjects well, and as an institute we make sure we cover all basics before jumping to core subjects. Clear? Pranav, Abhirup, and in fact we have planned a demo class for thermo also on coming Friday, guys. So the whole aim is to introduce our all mentors to you guys, so you guys get confidence. Yes, IGC is right place where we teach everything from scratch and our team teaches as best they can. Clear? Those who are watching this session, everyone, is it, this point is clear? The importance of having a team based learning, right? Because if one person will have certain limitation, right, or two-person, because all other institute other than IGC, you all know, right, most of the subjects are taught by only one person. None of the institute having team like IGC, subject expertise for different subject. Okay, and that's how our result is always better, and in fact non-aero students can produce best rank, like one digit rank. Sneha, you should have that inspiration of Mr. What is name, Anish, Ian guy from Calcutta University. In fourth year he got AER 17. He was an iron engineer. Or you should have inspiration of Mr. Shriram, with an EC graduate, could get AER 2. This should be again inspiration for all aero people also, those who join IGC. If non-aero students can get best one digit rank from IGC, why can't aero people? It's all about hard work. Joining IGC is not self-sufficient, Pranav or Nirja, Dhananjay, Anand, right? Because every year we see good number of students join IGC, but everybody is not studious. Abiru, okay, you know the fact. So once you join IGC, you need to work hard along with us, and then there is no doubt. We believe in 100% success rate. Whoever is sincere student in IGC, we make sure either Aero guy or any other branch which we teach, they should get success. Okay. Yeah, please access sir. Continue.
Yes. Okay. Yeah. So as I was saying, so all these parts we will be covering in gas dynamics sessions, where we will go deep into the subjects and we will understand what is exactly happening there, the physics of such flows. And when it comes to subjects like rocket propulsion and all, by the time like you will be mastered over those topics, and it becomes much more easier for you to grasp what's going on. And these propulsion or other subjects are the practical places where you can see the fundamentals that is being applied. It is good that in the aerospace we can see both physics as well as practicals in the subjects. That is very very interesting part. Okay, so now if I move on, so I'm really not going to deal with this derivation part, as I said earlier. So we can define a certain other parameters like a characteristic velocity or the thrust coefficient. So like we already defined what is thrust, and we already defined what is exhaust velocity and all. So now, so to define the thrust coefficient, before that, like we will define one more interesting parameters, just like how we defined a specific impulse, that is effective exhaust velocity to the gravitational constant. Similarly, characteristic velocity is one such parameter which is called as velocity because it has the dimensions of velocity, meters per second. So it is nothing to do with any actual physical velocity you can measure in the system. But so how do we define it? We define it based on the chamber pressure. What we call it as chamber pressure is the pressure at the start of the nozzle, right? So when you burn the fuel, so what you expect out of that, so you will be raising the system's thermodynamic property to certain pressure level P naught and certain temperature level T naught. Why do we need to improve the P naught? Because that helps you in generating the excess mass flow rate, whereas increasing the temperature will help you in increasing the velocity, because temperature is a direct measure of energy. So in the system, so temperature dictates the velocity at which the mass is ejecting, whereas pressure dictates the amount of mass that is being ejected out of the system. So that is why we usually rise the pressure and temperature within the system before it starts expanding. So that is what happens at the chamber. And so you see, it is just related to a pressure in the chamber and the area at the throat and the mass flow rate of the propellant which is going out of the system. It is not even talking about what kind of propulsion system you are using here. It is not even talking about what kind of nozzle geometry you are using here, except for the throat condition. And it is not even considering what kind of ambient conditions you are having. So it gives some kind of a comparative measurement among the different propulsion system. It may be a solid propulsion system or the liquid propulsion system or the hybrid propulsion system, it doesn't care. It is just the defined quantity, and it helps you in comparing a different propulsion units, right? So it has a unit of a velocity, that is why we refer it as the characteristic velocity. Okay, so now we can define our thrust coefficient. So the thrust coefficient is usually defined as a non-dimensional number that is defined as the actual thrust produced by the engine to the non-dimensional non-dimensionalizing with the inlet pressure times the throat area. So it has the unit of force. So we can easily define it. So and thrust can be written as mass flow rate times effective exhaust velocity divided by P naught 180. And just now we defined P naught 80 divided m dot is what? That is nothing but characteristic velocity. So we can easily write the thrust coefficient in this fashion, right? So being defined all these parameters and some important relations, so let us look into a few problems, one or two problems from previous year gate that is being asked out of these topics. Okay, so everybody clear now? So like, yeah, I cannot ask whether you are clear, but at least you guys are understanding the idea, right? Like how we actually proceed with the subject, what are the things we are going to see when it comes to a subject like rocket propulsion, right? Okay, okay, yeah, let us see one or two problems. So this one is a fresh problem from the gate 2024. It happened just last weekend, right? So they are asked to calculate a mass flow rate. So see, like these statements are not complete. We are yet to receive the official questions once the response sheets are out. But as of now, based on students' feedback, so we are just taking the numbers given in the problem, whatever they are remembering. So from that, like we are constructing the question, and we are doing here. So fine. So like they are asked you to calculate the mass flow rate. Say like I have a rocket system, right? So which is carrying certain amount of propellant mass, right? So that is burning and that is ejecting out of the system, say mass flow rate of the propellant, and which has a specific impulse of 200 seconds. Okay, so now which is producing the thrust of 60,000 Newton, and they are giving you the take gravitational constant to be 10 meter per second square, right? So now they are asking you to calculate the mass flow rate. How can we calculate now? So we already defined the thrust can be written as mass flow rate times effective exhaust velocity, right? Also we defined a specific impulse can be shown as effective exhaust velocity divided by G naught, right? So now you just replace this one here. So that becomes mass flow rate of the propellant times Is times G naught, right? So now write it for mass flow rate. So what do you get? Mass flow rate is nothing but thrust divided by specific impulse times G naught. So put the numbers. What you have? 60,000 divided by 200 into 10. So I am not even going to use the calculator here. 10 cancels, 200, 200. So 30, right? So you have 30 kgs per second. So you can check the units also. Thrust is having a unit of Newton. So Newton, that is nothing but kg meter per second square, and specific impulse has unit of second. Gravity has a unit of acceleration. So meter per second square. So meter per second square, meter per second square cancels. You are left with kg per second. Clear? The answer should be 30 kgs per second. Any doubt here? It was straightforward, right? Okay. So let us take one more problem. So this is from the rocket equation that we saw a few slides back. With a total lift-off mass of 10,000 kg, so they are given you the initial mass m naught moves vertically upward from the rest. So that means initial velocity is 0, and at a constant gravitational acceleration of 9.81 meters per second square, and it has a propellant that has a mass of 8,400 kg and burns at a constant rate of mass flow rate of propellant that is given 1200 kgs per second. So if the specific impulse of the rocket engine is 240 second, neglecting the drag, the burnout velocity in meters per second. So they are asking you to calculate the final velocity. So what is final velocity? So the delta V change. So that is the change in velocity you can expect is nothing but the final velocity minus V initial. So that can be written as using the rocket equation VE ln or Cj in general ln m naught or mf from the rocket equation that we just saw few slides back. So now it is given in the question that is it is lifting off from the rest. So initial velocity is 0. So the burnout velocity or the final velocity is this one. So how do you calculate this one? So we have a specific impulse that is related with the exhaust velocity Cj with G naught like this. So I can write Cj to be equal to Is times G naught. So you can replace here, and you are already provided what is an initial mass, that is m naught, and final mass. How can we calculate? We are given the propellant mass, so we can calculate the final mass as initial mass minus the propellant mass, right? So now everything is available to you. You can easily calculate, right? What is is? You have 240 seconds multiplying with 9.81 times natural log of m naught is 10,000 kgs divided by 10,000 minus 8,400. Right? So what you get? Anybody calculated? Yes? Anybody with the numbers? Okay. So you should get the final velocity or the burnout velocity to be 4245.9 meters per second. Okay. So that ends our discussion on today's demo session. So do you have any doubts? Yeah. So you guys have any concern or any doubts? Like you can reach even after the class. You can reach get classes at these contact details shown in this slide. Okay. Thank you guys. Dinesh sir? Yeah.
Yeah, we will wind up, sir. Thank you, sir, for your support.
Okay. Okay, sir.